Okay, so we got through what's becoming a less important part of this from just like the standpoint of the numbers of exoplanets that people discover. Doppler Shift was the first thing that worked. It's the, now if you discover an exoplanet, odds are it's through this other method, the transit method. But the important part of the Doppler Shift is that it's our way of getting into 3D, because now we can see things moving back and forth. And Doppler Shift everywhere, especially when we get to cosmology, will be really important. So this really adds depth to the universe, outside of the fact that historically it was the thing that got us our first exoplanets. Okay. So, again, just reminding you guys that you're very, very, very lucky, where for, 10,000 years people have been, totally intrigued by this question of, around each one of these stars, are they like our sun, and do they have planets, what type of planets they are? We're all the first generation to have a really good answer, and it's going to get better and better and better for this, so just kind of enjoy it, and nobody burned you alive for doing so. Maybe, in another decade or so, certainly we won't be having, Skyping with aliens or whatever, but the idea that somebody says, hey, I found this exoplanet and it's got an abundance of, complicated biomarkers, so-called biomarkers in the atmosphere, that might actually happen. So the first way of doing that, again, was through this idea of Doppler shift, where just like sound gets Doppler shifted, you hear something coming towards you, an ambulance, the siren seems higher pitched because the source is running towards the waves that it's emitting, so they seem to be crunched up and therefore a higher frequency, shorter wavelength, or if it's running away from you, it'll seem lower pitched because it's running away from its own waves. This works for light too. The only problem is that this is only really noticeable if you're moving at an appreciable fraction of the speed of light. So the idea of driving so fast you turn a red light green is not going to happen, and I encourage you not to try it. But for things in the cosmos, they move so fast that we actually do this. And the terminology is blue shifted if it's coming towards you. Doesn't necessarily mean that it's turning the light blue. It's just shifted towards the blue side of the spectrum. Red shifted if it's running away from you. And these used to be better names than they are now, because now they kind of, to say that infrared light is blue shifted, well, it's not blue in the first place. But just remember that blue shifted means running towards you, so the frequencies are shorter. Red shifted means it's running away from you, so the frequencies are lower, wavelengths are longer. And the way that this works in practice is not the thermal part of the spectrum, the continuous spectrum, which is in fact the light that you see. It's actually the light that you don't see in the absorption features that people use to detect Doppler shift. So these absorption lines, these really, really finely etched features, so there's hydrogen alpha, the famous hydrogen alpha line. And if you see this thing wobbling back and forth by some really tiny amount, which is what happened here, you can tell the star's moving towards me, away from me, towards me, away from me. If you see a star that's not in a binary companion, just all by itself, and it's wobbling back and forth by 30 meters per second or so over the course of a few days, then something's got to be pulling it around. And that something's got to be, based on the lack of light and the inferred mass of planet. So this is from, really hard work that culminated in 1995 of the first legitimate planet around a main sequence star. People had seen weird things before that through different methods, but finally Doppler shift got it. And Doppler shift at first got planets that just completely exploded the idea of the nebula theory that we use to explain our own solar system being the one and only thing that you could do. Because that story seems so sensible. This is what people in science call a just so story, where you take the data and then you tell a story about it and it seems good and you pat yourself on the back. And because this isn't really an experimental science, you don't make solar systems in a jar and watch them and repeat the experiment. It's kind of hard to tell whether or not you got it right, just by virtue of, the explanation seems legitimate. So our story was that only terrestrial planets would form near the sun, only gas giants would form far out because of this whole temperature of the proto-sun thing. And it seemed very sensible, but then the first ones we saw were these monsters, these hot Jupiters, which, in some cases were multiples of Jupiter's mass and much closer than, so this is the comparative solar systems, and this is all 1 AU, so there are these things 10 times the mass of Jupiter and about about the distance that Venus is away from its host star. And here's something about, 4 times the mass of Jupiter, closer than Mercury. So these things actually still defy complete explanation, where it's like, how are you getting what's obviously a gas giant to just remain in place at this absurdly close distance to its star without being completely blown away over the entire solar system? So what's keeping this thing alive? Some magnetic fields that are shielding it, or is it actually on its way into the star and it's going to die? Something destabilized it. We're seeing these things as they plunge sadly in, so who knows? So a little bit unclear as to where they're from. They're the first things and the weirdest things that people saw. Getting better, we can see things with smaller signals from like 50 to 100 meters per second down to 1. To put it in perspective, in order to see a planet like Earth at our distance with our mass, we're pulling the sun around our sun by 3 centimeters per second or so. And that's kind of bad, so that's, still orders of magnitude below this. But what makes it even worse is how long would you have to sit there and wait and watch the sun from, imagine that you're an alien on Alpha Centauri and you want to figure out if there's a planet around our sun. So you're sitting there and you're watching it, and if you want to observe something like Earth, how long do you have to watch to see a full period of this? A year, right? So the time and the precision are both pretty limiting factors. And these things are all described in terms of so-called phase, which just means they put a whole full period on a single graph. But these are days. So these are 10 days, 20 days. In the case of Kepler, most of the Kepler planets are 5 days, 3 days. And you'll see that when you plot this on exercise 8. So that's Doppler shift. Just remember that the idea of Doppler shift is more useful than just finding exoplanets, or at least getting us started, and we'll come back to it a lot. So any questions about that stuff? Okay. So this was the drink from a fire hose, and the second method, these are total cartoons. But if you remember the picture at the beginning of this lecture where just very sneakily Mercury was blocking a little bit of the sun's light, and it almost looked like a sunspot. Now, granted, Mercury is a tiny planet, but you can do this. You can just look at the total amount of light coming from a star, and if the total amount of light coming from a star dips, comes back, wait, 3.2 days, dips, comes back, wait 3.2 days, dips, comes back, same amount. Every 3.2 days, there's a totally identical dip in the sun's light that maybe looks like this. So this would be the total amount of light coming from the star. And to put it in, I don't know if you can see it in the back, this would be all of the light. This is 0.4% dip, and we're here. So this is maybe 1/10 of 1% of the total amount of light coming from the star varies. So what must be doing this? What's causing the total amount of light from the star to just dip, dip, dip at very, very regular intervals? Probably something that's not emitting light of its own. So this is what we call transit, after exactly what it is. So when you see Venus go across the disk of the sun, that's a transit. And we see a little bit less sunlight when that happens. So these are the light curves. Each one of these is a data point over, I don't know, maybe an hour, half an hour, something like that. Where do you think you have to be to do this successfully, to have such stable seeing where none of this light is being absorbed or scattered, or you get this wonderfully flat, even curve? So this data probably comes from space. So these are all satellite pictures, and this is all from a dedicated satellite called Kepler, where people had, basically proven the feasibility of this from planet Earth, but then said, if we're going to do this right, we're going to have to make a satellite, and we're going to sit and point it in, a patch of the sky and have it unblinkingly stare, in fact, here in Cygnus. So Kepler, for 3 years, just stared at this patch of sky with, 250,000 potential planet stars, really dim stars there, and just measured the light coming out of those stars, constantly integrating every half hour or so. And this is Kepler. And Kepler just finally blew its last flywheel, which is the thing that keeps a spacecraft stable, so it's done with its mission. So works in visible light. It's incredibly optically stable. It's above the atmosphere, and it has a really wide field of vision. So it's able to resolve all of these stars, and there are over 100,000 potential stars with planets around it. So this was the drink from the fire hose. Yeah. Yes. So do you mean, does Kepler know? So yeah, this is why these cartoons, I wanted to make a point that they're cartoons, is that this is what you get. So all you see is light, 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 and these are all normalized to say like the total flux from the star. So light, 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 dip. And there's a little bit of stuff that you would have to kind of piece together is if this transit is shorter, is that because the planet is piercing this lower limb of the star? If the transit is longer, is it because it's going that way? Is the transit longer because the planet's moving more slowly? So you don't really know. All you do is you see starlight, and then the starlight dips. And you can figure out some things. So for instance, you can go back and look at the star that's hosting Kepler 4b, and you can see, oh, it's a main sequence star, it's a K5, therefore I know its mass. Therefore I know, how much gravitational pull it should be putting on this thing, and then you know the period. So you can do exercise 5 kind of stuff and find a little bit of information about the planet. Actually, to be honest, the surprising amount of information about the planet, mass, and stuff like that. But there's some things here that are, I don't know. Like, I don't know exactly where this thing is crossing. They all, in your head, they're kind of going like this. They could be going like that. You don't know if they're tilted this way or tilted that way. So there's some things that you'll just never know, because all you see is light, dip, light, dip. Yeah, so the period is every 3.2 days the dip occurs, and the dip itself would be for like a couple of hours. So over the course of a couple of hours, this planet is slowly transiting across the face of the sun, star. And during that time, planet's dark. It's actually covering up, blocking up some of the light. So 1,000th of the light coming from the star is now hitting the planet itself, and you don't see it. So something like this, if you had a bigger planet, you would see a bigger dip. So imagine something bigger is trundling across the disk of the sun. It's blocking more light, so the dip is bigger. So the things that you can figure out is based on the size of the dip, you can figure out the size of the planet itself, assuming the planet's like completely dark. And then if you do some follow-up observation and you look at the star itself, you're like, oh, well, it's an M star, so I know its mass, and I can figure out how much it should be pulling this thing. But the good news is this spacecraft just, again, looked at over 100,000 candidates and just sat there for 3 years pulling light from it. And at first you had the same sort of biases as you would tend to see bigger planets, you would tend to see them closer. In this case, just because at first Kepler, is seeing things that repeat every 3.2 days or so. So obviously it's really close if it's orbiting every 3.2 days as opposed to our 365. So the first Kepler candidates, low numbers, Kepler 6, 5, 4, they're still what you would call hot Jupiters. And to put it in a little bit of perspective, on some of these things like Kepler 8b, iron is molten, so that's completely insane. But it's getting better and better, and in the kind of later days of the Kepler mission, it was getting down to things that look suspiciously close to Earth, and you're free to wonder what the composition of this thing is, which we'll talk about later. So Kepler 4b is about 4 times the radius of Earth. So what do you think it is? You think it's like something like Neptune, or like a big, big rocky planet, or a little gassy planet, or none of the above? So finally, the later Kepler candidates started getting smaller and farther out as the time that it was sitting and looking got longer and longer. And then this. anybody hear about this? It's probably like 4 months ago. This, not the Planet X thing in our own solar system, but the alien superstructure that was passing by a star. Show up on anybody's like Facebook newsfeed or something. Okay, it came from Kepler, and Kepler looks at so many planets that their machine algorithms, computer programs that sort through and say like, oh, you're a transit, you're not a transit. And so it misses oddballs, so it misses freaky things. So there's a citizen science project called Planet Hunters where like school kids and stuff like that, they look at these spectra manually because there's some things that human eyes are always better at doing. And they found this. So this is the light curve from something. And it started with, and the reason it got identified is that looks like a transit to me. So this is, 1%, so the total light. This would be 5% of the light. So this would be this monstrous planet that's, about 20th the size of the star itself. So this would be 1%. Even 1% is really big by the standards we were talking about. So on those previous graphs, those dips were like 0.1, 0.3, 0.3, not 1 or 3. So this would be a hell of a transit. And then this happened. So that's 15% of the total starlight is obscured. So this would be something about, a sixth the size of the sun, blocking out all the light. And then this happened. And they're not sharp. There are these weird structures to it. So, of course, immediately people make the sanest conclusion possible that this is a giant cloud of alien superstructures that floated in front of the star. So probably not, but there's still, nobody knows what this is. So it could be like a cloud of comets. It could be some, freak event where a little bit of dust was just in the right place and it was like much closer or something like that. But it was totally identified by like random people in the citizen science project. I'm going to make you guys take part in, or let you if you want to do the extra credit, in the Galaxy Zoo one, which also identified weird stuff. But that was totally a Kepler thing, and nobody knows what this is yet. So 20% of the light from the star just like blocked out. So imagine the size of something to do that. So if you're on Mars and you're watching Earth pass in front of the sun, it removes like 1/10 of 1%. Crazy. So that's the transit method. It's Kepler blew its last gasket, so it's kind of done, but we have enough data from it, which is kind of exciting, and tell you like some of the statistical results, but honestly, like every 2 months, the conclusions from the stuff totally change as more people do more analysis and more planets get published. So any questions about transit stuff? The humble transit that we talked about back in like exercise for lecture 5. Yeah, so this would be like 20%, 10%. So we're 1/100th of the diameter of the sun, but then area, which is what you're seeing, goes like squared. So 1/100th squared is what we would block out, which is much, much less than 20%. So this is something that's basically, if somebody painted an M star black and passed it in front of our sun or something like that, they're kind of crazy. So maybe Pythagoras was right. There's an anti-sun. Yeah, weird. And there's a third method, mostly because I like writing multiple choice questions in groups of 3. No, it's actually serious. There's direct detection, which is kind of what people want. This really kind of, sneaky, indirect, we see Doppler shift and infer planets, or we see dips in light and we infer planets through the absence of seeing them, seeing stuff. Kind of bugs people. What you'd really like to do is this Marvin the Martian thing where you look through a comically oversized telescope and see a dot of light and then wonder about, who's hanging out on there. And people do that. It's really painstaking. This is one of the more famous ones. So there's an aperture over this. So this is a star Fomalhaut b, and they've blocked the light from the star itself. And Fomalhaut happens to have this huge dusty plane, which helps a bit too. And the claim is that's a planet. So that's a direct image of a planet around another star. Do you believe it? What would it take for you to believe that that's a planet? let's say you got plenty of time, and you know the mass of this star. And you did very well on exercises 4 and 5. I don't know, let's say it's pretty far away. And in fact, these things are pretty far away, so this is really nice. One of the reasons people like direct detections is it kind of picks up the slack for transit and Doppler shift see big, close things. This tends to see things that are much farther out. So this is like, maybe Jupiter distance, like 5 AU or something like that, maybe even farther. Where would you expect it to be in 2 years? So somewhere along farther in its orbit, right? If you knew Kepler's laws, would you know exactly where it should be in 2 years? Yeah, because you know the mass of Fomalhaut. So the argument that this thing is actually a planet, which I still think is like very shady, but people have kicked the tires on this, is that this speck, that's the speck, this is it blown up, it's moving in accordance with Kepler's laws. So, and it's not just like crap luck that maybe the speck just happened to show up a little bit farther away. So the direct detection, and you can, if you can isolate it, you can do a little bit of spectroscopy and say, actually it's emitting infrared light like an exoplanet should be, like Jupiter, for instance, would be. These are really hard fought, but the good thing about them is they're far out. They kind of fill in the space of all the exoplanets that we see, and maybe people would be better at this in the future. So yeah, this is definitely the hardest way of finding an exoplanet. Okay, so this is where we are now. Remember, the first one was discovered, first exoplanet around a main sequence star. There are these crazy pulsar planets people saw as early as the late 80s. But as of a couple of days ago, 3,412 planets, 2,551 planetary systems, including almost 600 multiple planetary systems. The Kepler data set is still being mined, and there are still the planet hunter people. I think that 1,000 should drop a bit. There are some people who just keep them all online, so you can search through this catalog and try to find a new homeworld when you get sick of this one, if you'd like. And the big thing that happened, I'll point this out because this lecture was supposed to be given on February 27th, 2014 when I taught it. And so fortunately somebody randomly said, hey, did you hear about the Kepler thing? Kind of embarrassing, is they actually in one shot announced 715 new planets. So in one day, Kepler just said, hey, the Kepler mission said, hey, we've got 719 more validations, which was crazy. And this is what the discovery chart looks like. Is 1995, 96, 51 peg, and then these are the Doppler shift methods, which is really painstaking. And then this is transit. So transit is basically taking over. And if there's another, Kepler 2.0 mission or something like that that's sent up and announced, you can just imagine what this is going to be like. So, if you know stuff about exponential growth, you can imagine what the prospects for exoplanet hunters are during your life. So you guys will be like absolutely lousy in data about planets around other stars. Okay. So the bit of statistics that you can get from this is that at a minimum, so this is conservative and even this is out of date, it's so hard to keep up, is that the typical typical star in our Milky Way galaxy should be a multiple planetary system. So it seems to be like if you do the kind of filling in the gap of the statistics is that just about, find a star, it's got a couple of planets. So we have that basically confirmed. The assumption that you're making is Kepler and Doppler shift. We're actually really only seeing stuff in this local neighborhood of the Milky Way galaxy. And we're assuming that we're not in a special part of the Milky Way galaxy, which we'll actually talk about when we start exercise 9, whether or not we're special. Of course, the answer is no. So pick a star. It's got multiple planets. Remember this wildly out of brightness scale picture. This should be millions of times brighter than it actually is. It's just hard to put that on a picture. Do you think there's some sort of selection or skew among which stars have exoplanets? So who do you think has the most or least? and why, if any? The O stars eat their exoplanets? Yeah, that is very reasonable. Any other thoughts? Oh, yeah. Got 10 million years, and we've been around for 4.5 billion years as a planet. So, yeah, that too. Yes, the other thing is that there might be a little bit of selection bias, is that it's much easier to see a K star wobble, for instance, than an O star. But yeah, it seems like the O stars, either we don't see them, which could be part of the effect, or they're so short-lived and they shine so brightly that they probably blow away their planets before they even have a chance to form, or they eat them or something like that. So around the high mass stars, you typically don't see too many. Unsurprisingly, if you take spectra of stars that have a lot of planets, you tend to find a lot of lines. So they're really enriched with metal. So very metal-poor stars just have less stuff to nucleate into planets. So more metals, more planets, stuff like that. And none of this was particularly, exciting and wild. This is the sun spectra. We have no spectra of this quality for other things. But yeah, we're a very, very metal-rich star. Yeah. This is the artistic representation of the spectra, is that if you looked at a metal-rich star versus a metal-poor star, and if you remember the intensity diagrams, the metal-rich star would just look scruffier. So there'd be more, more wiggles. And a metal-poor star, you would just have fewer lines. You'd always have hydrogen, for the cooler stars especially. For M stars, you even get molecules like titanium oxide, which cut so many lines into it. But it's basically the spectrum would look smoother for a more metal-depleted star. And also, I'll say this, because Dr. Wick is not in the room, is that the periodic table to an astronomer is hydrogen, helium, and then everything else is metal. So everything but beyond helium is referred to as a metal. So when people say metal poor, metals include like beryllium and calcium and stuff like that. So it's really easy to take a chemistry exam for an astronomer. It's 3 things. So this is the selection bias, and this is to put it in perspective and see where we're going. In fact, this is actually pretty old too. It's really hard to keep up with this stuff. So even this 2-year-old chart, maybe 3-year-old chart, this should be filled in a little bit lower down in size of planet and also a little bit farther out in distance. But this is kind of a scatter chart of the exoplanets that people see. And this would be the mass in terms of Jupiter masses, and this would be the distance from its host star. And yeah, you see this kind of hot Jupiter bias. Those were the original Doppler Shift detections. And then you see this desert start to be filled in. This is the Kepler data. And it's going to get better and better. In fact, it's already better and better. And we definitely don't see things which totally exist. So do you think that there are no planets like Uranus and Neptune out in the cosmos? Probably not. I don't know why they wouldn't exist. So why do we have no dots here? It's just these are hard to see at the moment, and in 5 years there will be more there. So realize that this represents like a complete selection bias. For instance, imagine that you're an alien and you want to know the average height of human beings, and just through really bad luck, you walk into like the lounge at a racetrack where the jockeys hang out. So you'll have like really bad data on human height. So because we see close planets and massive planets, is that this is biased. This isn't the real truth. And there are these schemes to tell you what these infer about the stuff that we should be seeing. In particular, there should be about 40 billion Earth-like planets in our galaxy. 40 billion. So and then there's this is the other kind of figure of merit, is that these 2 green lines mark out something where people really want to do a lot of searching and find planets, the so-called Goldilocks Zone, where you're able to have liquid water. It might be people actually refer to it in academic papers like this too, and it might not have like complete cultural relevance. So what makes something the Goldilocks Zone? Anybody who's not, yeah. So for anybody who's not heard this fairy tale, it's about this young woman who breaks into the house of some hardworking bears and eats all their food, and some's like too hot, too cold, just right. So not too hot, not too cold, just right for liquid water. So you presume that's where life would be. Okay, so something that's a little bit more exciting than just stars have lots of planets is that this is kind of to scale, as good as I could make it. We kind of live in a bimodal solar system, right? So we have big gas giants, and then we have little terrestrial planets. And one of the things that wasn't even questioned because nobody had the, either creativity or knew that this was a valid question to ask, I guess, is that do you think there are planets in kind of a middle ground? So, this is about 10 times Earth's mass, 300 times Earth's mass, about 5 times Earth's mass, 7 times Earth's mass. Is this like the way that things have to be, or is this some middle ground where maybe it's true that you need this much mass to keep a gas giant, enough gravity to pull the gas on or something like that? And it turns out we are actually kind of in a lucky solar system. And what's true is that there's a smooth curve that connects things like Jupiter to things like Earth. And we just, through whatever luck of our formation of the solar system, we didn't get any middle things. And there are 2 classes of planets out there. So terrestrial and Jovian. There are actually 2 other types of planets, classes, that we just don't happen to have. And that's now been well established as of, as recently as a couple of years ago. And they come under the names, and this is kind of a guess about their composition, but a very good one, is that they're super Earths and they're mini Neptunes. And the super Earths are maybe like, about twice the diameter of Earth, probably rocky, possibly have a huge sheath of volatiles or water on it, so like water worlds. And then the mini Neptunes are a little bit smaller than the gas giants, and they probably are also water worlds, but they also have enough gravity to have this giant envelope of hydrogen and helium on them. So these are things that have no analog in our solar system. And this is, again, so 2 years ago, people realized, like, holy crap, there's all this stuff out there, and we just happen to, in fact, we're kind of lucky because we have quite a lot of gas giants and other few terrestrial planets. So you just happen to not get a mini Neptune. It's kind of a bummer. Or a super Earth. Okay. So the questions about that? Okay. So the thing about the Goldilocks Zone and habitability I just want to mention really briefly is that the backstory of all of this is, we're probably not going to go out and colonize one of these things. Is, even if you don't say it, in the back of your mind is really, we're looking for life around another planet. So that would be really awesome. And if nothing else, there's a class of people on planet Earth who you could just totally poke them in the eye with this discovery. And it seems to hinge a little bit on finding liquid water, like even in our own solar system. Europa, liquid water, will go, drill down and put a little probe through and see if something licks the window. But it doesn't necessarily have to be that way. So we have this almost chauvinism about photosynthetic, water-loving life. And even on planet Earth, so you get what could almost be considered to be kind of a second, totally separate branch of life that doesn't necessarily need photosynthesis. You could do this underwater, under a sheet of ice or something like that, outside of the Goldilocks Zone. These are black smokers on the bottom of the ocean floor. And it's just chemically enriched goo kind of bubbling up from the ocean floor, and there's life all over it, right? And actually, anybody know where this is? Yeah, Yellowstone. And each one of these different colors is a different type of bacteria. So also, they thrive on heat, so they actually use just heat to make a living. So you can, even on Earth, there's some evidence that this idea of life is like plants and animals. We can extend that a bit. And part of this is crap that I found on DeviantArt. Part of this is, like, people actually thought really seriously. So could we have life on Jupiter or something like that, And Jupiter is pretty far outside the Goldilocks Zone, but Jupiter's really big, so it's got a lot of thermal energy. And the idea that they came up with is, sure, there would be these like gas manatees that float through the huge Jovian atmosphere and eat little bacteria, which are again also make a living by harvesting heat. And I don't know what that's about. But it's basically like the universe is probably more creative than we are. So this idea of pinning all of our hopes on liquid water and liquid water, liquid water, there could be something else out there. You really just need chemical enrichment and a source of energy. Yeah. You mean, yeah, sure. Yeah, that's kind of the us going around and contaminating stuff. It's actually a weirdly um, people might not realize how valid that question is because does anybody know about helicells? Okay, this is the weirdest thing ever, and I'm proud of this because I'm also from Baltimore. Is that this poor woman with cancer and multiple STDs was basically used as a medical guinea pig, and her cancer cells don't die and the DNA don't degrade. So Henrietta lacks, and so there's this strain of cells called HeLa-cells, which basically infect every single lab ever. Like the universe, the Earth is now covered in HeLa-cells. They're like everywhere, and they're new life form, which apparently you make in a very terrible way. They're HeLa-cells on the International Space Station. Like you cannot decontaminate without just autoclaving everything. So when we land on Mars and we start scraping around with petri dishes, I think there will be HeLa-cells in them. So you just trust that people are, from a scientific perspective, you trust that people are clever enough about sterilizing stuff that they don't, introduce a contaminant. And it's kind of an understood thing. It was pretty wild. I don't know. There's a biography of this person, and she's immortal. So it's an immortal line of totally non-degrading, endless cells that contaminate everything. It's really wild. No, in the sense that if you're looking for microbial life, um, microbial life is big enough to identify. And in the case of, for instance, I know that the contaminant would be HeLa-cells just because they contaminate everything. Is that we know what they look like, right? And in fact, that's not what you're going to be seeing in the case of Mars or someplace where we would actually go and actually find a sample. You would find maybe these little grains of something fossilized inside of a rock and say this is primitive bacteria that got kind of stuck in here. So yeah, to find living things on another planet, like we would maybe have to wonder if we introduced them, but I don't know. Yeah. Any other questions? Okay. Since we are talking about life on other planets, I'll just remind you of this, which is kind of a buzzkill. And it's good because Dr. Work talked about this on Friday, is that Carl Sagan's idea of the cosmic year, just to put some perspective on our interactions with potential life on other planets, is that put the Big Bang at January 1st, and then now is midnight December 31st, and it just gives you a sense of cosmic time. And so September is when Earth forms, and then by by September 22nd, you get microbial life. By December 17th, people figure out this, or life on Earth figures out this innovation of things like shells and teeth. So the fossil record actually just blows up, called the Cambrian explosion, because you have stuff that can be fossilized. December 26th, dinosaurs. December 30th, no dinosaurs. Dinosaurs are by far the most successful thing that have ever walked on planet Earth. And then now humans show up 2 minutes to midnight. They figure out that if you put seeds in the ground, it makes food 25 seconds to midnight. A second to midnight, we figure out that we're actually orbiting the sun. So think about astrobiology in that context. And if some star forms, a couple million years before we do, or they're a day, even just a day advanced or retarded on the cosmic calendar than we are, well, what does a day do? A day gets you from dinosaurs to us. What about a week on the cosmic calendar? That's the Cambrian explosion, where you have trilobites suddenly evolving, and that's the great innovation to us. So this idea that this federation of planets were all basically the same thing. You have like the same moral compass, but some of us have like a skin condition or whatever, and we all kind of work it out, is pretty unlikely. So this would be like going to a movie theater and everybody inside the movie theater, all 150 people, have your same birthday and down to the second or something like that. It's so unlikely that anything like this is a possibility. So odds are, just give people like a month or something like that, a cosmic month, and they would be well advanced beyond this. Which leads to something called the Fermi Paradox, is that if there are so many planets and there are so many, sun-like stars, and there are so many chances to have habitable life, well, where are all the aliens? As it turns out, the timescale to evolve and the timescale to go from planet to planet actually are pretty mismatched too. So you'd actually expect to see one successful species basically colonize the galaxy. We could be it, though. So they're, not really fundamental part of the course, but it's like this is the time to talk about it. And the way that people talk about it is the so-called Drake equation. I'll just leave it up. It's a way of phrasing the discussion. I will say if the idea is that this would be the number of communicable, intelligent species out in the galaxy. And it gets broken down into some things that you could kind of like, oh yeah, like the number of Earth-like worlds per planetary system. We're on the verge of figuring that out. This is progress. Fraction of stars with planetary systems. We figured that out. It's 1. So in the time since Drake wrote this down, we've made some progress. But I will say that if even one of these things is totally unknown, then forget about it. But you'll see this from time to time. I will say on Coursera, there's a pretty good course on astrobiology, the actual practice of astrobiology, and less sci-fi, more, what it comes down to a lot is understanding a lot of chemistry and how you would find chemistry in planetary atmospheres using the classes of telescopes we have now. So just leave that. So any questions about exoplanets and stuff? Yeah. Yeah. Doppler shift is kind of an observing phenomenon, and Doppler shift doesn't enter into the fundamental physical restrictions on how fast you can travel. So what Doppler shift would do, for instance, is imagine that you left this far-off star and you're coming towards Earth, and we see you, right? So you can't travel faster than the speed of light, so we see your ship before you get to Earth. That information would look really, really funny, where we would see it and your spaceship would look like super blue, and then it would also look like the time, the sequence of you coming towards us would be a movie played 10 times too fast and very blue-toned. But it doesn't represent like a restriction on how fast you can go. It's just the... I wasn't saying like... So, go on as fast as... Right, so there's time dilation and special relativity, and it's not Doppler shift, but that's exactly what you're thinking about, is that it's the same trick as in fact, special relativity, if we had more time to talk about it, would be the thing that we cut our teeth on before talking about general relativity, is that same deal is that there's no such thing as a universal clock. So if we all have clocks and we sit here in this room where we're all moving at the same speed, basically, and we sync them up, and then you go and you fly by a black hole, and I get on a rocket and I go at 9/10 of the speed of light, and we go in these kind of speed of light and massive black hole style adventures, our clocks will go wildly out of sync. And when we get back to the classroom after our wild adventures, some of us will have out of sync clocks, some of us will look really old, stuff like that. But that's just garden variety relativity. Well, garden variety. And Doppler shift is just how you would perceive the light itself. So it's true what you're saying is that if we're on the spaceship going at, large fraction of the speed of light, is that time will seem funny, but you actually win because your time in the accelerated frame goes more slowly. So it'll seem like, boom, I'm at the far off star. People in the far off star will have been like, we aged an incredible amount while you were traveling here. And you're like, well, I didn't. I was on my spacecraft. So if you're accelerated, you actually travel.
Where he would go. Still the same.
That sounds right. Which one was that? Oh yeah, I just watched the Charlton Heston one. Yeah, that's okay. I don't know. Why would you remake a movie with Charlton Heston in it? Seems crazy to me. Yeah. Any other questions? Okay. So give you guys time to work on exercise 8 and then spend a little bit of time talking about the